All right. Well, good afternoon, everybody. Welcome to the last week of official lecturing in CS164. Before we start, do we have any questions that you'd like to ask? Not that we have too many people here as usual, but there you go. All right, well, seeing no hands, I will proceed. We have a couple of, I've just collected a couple of random topics, only loosely related to the rest of the course, but that just seemed to be reasonable things to do in this last week. On Thursday, we'll just do a summary of the course for those of you who are interested, and I will answer any questions that people might have, either about the course material or about Project 3 at that point. Speaking of which, I hope everyone's having a fun time completing the project. We will announce details about the tournament in a bit. All right. So two unrelated, but I think moderately interesting topics that I'd like to cover. First of all, in static program analysis. And second of all, in runtime, another runtime issue. Just an introduction to both. Those of you who have taken CS61B with me will have seen the runtime material before, because interestingly enough, data structures are actually useful in the implementation of programming languages. But let's start with some static analysis. All right, so again, just sort of a review here, we're interested in determining runtime properties of a program, things that are true at execution time, but can be determined, can be predicted to be true at compilation time. So is a particular variable always the same? Does it always have the same value? Is it a constant, for example? Now, the point, of course, is that we must consider all the possible program executions, somehow summarize them in order to do this kind of analysis. And we are going to do this, as always, with these kinds of static analysis. We're going to err on the side of caution. We're going to make no assumptions if we can't prove that something is true. So if we are allowed, for example, to say the conservative position is to say that X could change at any time. So we're allowed to say that it's not a constant even when it is, but we can't say that X is a constant when it is not. The reason is that we use constantness as a property that has that's useful for generating good code, for example, or for demonstrating that your program always works. Non-constantness or guaranteed non-constantness is not particularly useful, and we don't use it. We don't rely on it. So again, there are many reasons why we might want to do this kind of analysis. We might want to do it to make our programs faster, optimization. We might want to do it to make sure that our programs work correctly, verification. And we might want to do it in some cases just for the sake of compilation, in other words, to determine whether certain properties that the language nominally requires are actually met. An example of the latter is Java's determination that you always initialize a local variable before you use it. All right, so let's take a look at this problem, optimizing virtual calls in Java. This is a client application, if you will. We want to find out, we'd like to know whether a particular call site in the program is always going to go to a predetermined or a predictable place. And as you know, because of dynamic method dispatching, a particular call, x.f of something or other, for example, could go to any number of function bodies. And we have to do some stuff at runtime to determine which of those it is. Namely, we load from the virtual table and all this sort of thing. We add several instructions to the sequence that branches to that particular function. So what we'd like to do is to see if a particular call site always, in fact, has the same dynamic type, or at least always dispatches to the same method body each time. So if there's a single target method, then we can simply substitute a call to that an ordinary call to that target, which uses fewer instructions and less time. Now, granted, the time required to actually do a call is not all that great, but if your method is short and you're executing it a lot, it can make a difference, a noticeable difference. Now, we can't tell what the type, obviously, but the type of a given value is from the static type of its pointer variables because of subtyping. You can have any of a number of different subtypes be applicable at a particular call site. So we have to analyze something about the execution, the possible executions of programs in order to do this determination. So for example, in this particular collection of definitions, yes, I know it's not quite in the right form, but you get the idea. We have two classes, one of which overrides the method foo. Class B overrides the method foo. We have a call in this function. We have bar here, and bar calls a.foo, knowing only, as far as the compiler is concerned, knowing only that a, the argument, is in fact of static type A, which means it could be of dynamic type, either A or B, and therefore it could go to either of the two bodies for foo. Now we see over here that I've declared a variable, a new B. I've assigned that into an A variable and then passed that to bar. So for this particular program, if this is all there was, then you know that this call up here is always going to go to the same method. And the question is, what property can we look for in the program to demonstrate that this is the case? Here's another example of how it would be useful to get at a certain nominally dynamic property with some analysis. So we have a cast in Java. You can write this if E, that essentially translates to something that looks like this. If E is not an instance of foo, so when I translate foo of E, convert E to a foo, if E is not in fact an instance of foo, and we're assuming here, obviously, we're dealing with reference types, not integers. That's a different kettle of fish. If E is not an instance of foo, then we throw this class cast exception. That's basically what the runtime system does, and it has some sort of a test to this effect every time you do this cast, because the cast doesn't actually do anything except check that the type is right. Now, with the help of generics, a lot of these casts that the programmer used to have to write in the bad old days of Java 1.2 or whatever it was, go away. You no longer have to, for example, you can have a list of strings rather than just a plain list, which is always a list of objects. And then when you get a string out of that list, the compiler knows it's a string, and you don't have to write that. You don't have to write paren string and paren list.get of something. Sorry about the construction noise, but it makes a nice background. So that helps readability. You can understand your programs better, but underneath, the implementation still does this cast. It actually generates, or it still generated that code. And the reason has to do with certain problems that are caused by Java's generic model. Because it's backward compatible, it causes certain problems. There are certain possible holes in the model, and you've got to do something about that. Okay, but what I'd like to do is to prove that no exception is going to happen at runtime, which means that I don't have to do this test anymore. So here's an example. I have this class, which is missing a right squiggly, sorry about that. And I have a few, I've declared a couple of simple containers. And I've put, and like this. And I'd like to know, and in this particular case, when I do c1.get, I know that what's coming, even though the type that I'm storing inside a simple container is type object, I know that this get is going to give me a foo, because that's the only thing I've put into this thing. Whereas C2, obviously the check is needed in this case, would be needed in this case, and it would fail. If I had tried to do the same thing, foo of C2.get, that would fail. And so the question is, what do we have to check in order to see whether this works? Here's another example. We would like to know, here's a program that has a loop, j equals 0, j less than d.len, and so forth. We throw an exception if this condition here is satisfied, and then we do a assignment into something called e.data, using e.len as the argument, and then we increment e.len. Now, the question is that we do have to assign to and fetch from e.len because we keep changing it, but we don't change d.len. Therefore, we shouldn't have to check it every time we go through this loop. We shouldn't have to fetch a new d.len. It's a constant. Now, in order to understand all of these things, we have to understand how the pointers that we are dereferencing sort of, if you will, flow through the program. In other words, how their values propagate, what variables take on what pointer values, and what these values point to. So what I'd like is a way of sort of tracing the flow of values from new foos, from new statements which create new objects, to things that dereference them, like myfoo.f dereferences a foo. Now, this isn't particularly, it's not particularly obvious how you would do this in general, because a pointer can flow by many different ways, not just assignment of local variables, but it can also go into the heap. And of course, you know, there's aliasing in that case. You can have several different variables pointing to the same object in the heap. How does that work? So anyway, it's not immediately obvious how you do this. Well, okay, and furthermore, I'm going to simplify my problem by not worrying about reflection. Now, for those of you, I hope many of you are familiar with this term, but in Java, you can do things such as ask, what is the class of this? You can look at the class of a variable. You can ask what methods are on that class. You can do all kinds of things like that, which really screw up compilation if you use them over much. But so we won't worry about that this time. Okay, so in the case of the first client that I showed you, where you want to know whether a certain method is always the same body, we must ask which new t's go to a p of which we are doing p dot foo, right? So which is there, which of the two types that we had, A and B, provide the value for a receiver at a particular point. For cast verification, that is making sure that a cast is going to work, but we want to know what values, how a particular value came about, what type of value came in, like what news were applied to it, and what casts it resulted from. So a variable that has been assigned from a cast, you know that its dynamic type is now conforms to that of the cast. And you have, again, with making sure that two fields are not the same field that you're assigning to, we have the same question. Just in case that wasn't clear, by the way, for that last one, the point here is that D and E are definitely not the same object. Therefore, the D.len must be distinct from E.len. We know that because E.len got created right here, D got created somewhere else, and we never do an assignment to D. So we can think of this analysis that we have to do as a kind of constant propagation. So, and if we look at if we look for the moment just at statements that contain new and assignments, so P equals new something or P equals another variable, we can ask at this point, for example, what possible types could R have right here? R's value has flowed from P, and P's value has flowed from here. Now, as you can see, in this particular case, we know that the only possible types for R are T1 and T2, which may or may not be useful information. So we imagine that we have reduced our program to something like this: P equals O1, else P equals O2, where these are origin 1 and origin 2, if you will. And then, so these are two symbolic constant values. And what we're interested in is here, what possible constant values, O1 or O2, could R have at this point? Well, these constant values are what we think of as abstract objects. Perhaps you remember that I referred to an abstract domain when doing some of the optimization stuff. We're doing the same thing. We're collapsing all the possible values of the program down into just a few. And O sub I then stands for all of the objects that might be allocated or created at a particular site, at one particular site in the program. So every new instruction, every new expression has its own number. All right. So if we have an analysis that creates a variable P, and we say that it has value 07, what we mean is that its value was created by this new expression, which I've sort of subscripted with a 7 to indicate it's the 7th new expression in the program. Okay, now we want to do something with references. Why do we have to consider multiple objects being allocated with one new expression? Well, a new expression can allocate any number of objects. I'm not quite sure I understand the question. I'm reading a question from the chat here. Not quite sure I understand the question that's being asked. There are multiple objects, but since they're all the same type, for the sake of this analysis, that's really all that matters. We don't really care that they're different objects. What we care is what their type is. So if we're going to analyze a program like this, where we've assigned to fields in the heap, we're going to have to keep around some notion of abstractly what's in the heap. So we know that y and w, if we can ask whether y and w point to the same object, we can ask whether z and y dot f point to the same object, and so forth. We're going to have to maintain that information. Now, you can see this could get rather complicated and expensive. So we generally, in order to get a little information, at least some information, we make all kinds of compromises. So it would be nice, in fact, as if we could keep track of the heap state or whatever at each point in the program, but and just sort of track it. That's what's called flow-sensitive analysis. Unfortunately, when you're dealing for this kind of analysis, you have to deal with an entire program, not just one function. And therefore, we have to be, it turns out that particular attempt would lead to rather vast complexity very quickly and very slow compilation. So we typically don't do that. Instead, we compromise in various ways. So, for example, we can ignore the flow of the program entirely, doing what's called flow-insensitive analysis, in which we assume basically that the program could be executed, the statements of the program could be executed in any order whatsoever, which you might wonder that you can get any useful information at all, but sometimes you can. I mean, sometimes you can, and that's what we'll look at here. So a program that looks like this, where we have two different assignments to P in different branches of the program, instead looks like this, becomes something like this. These are all the places that involve P. They all sort of collapse to this one little point that represents the state of P at any given time, or the state of P. Okay, so this is sort of a version of the program state at any given time. It's because it doesn't take control flow into account. We say that it will find for any particular variable all of the possible values that the pointer might have. And so if it finds that if there's a certain value that a pointer might not have, it will reliably determine that information. So this is a very imprecise sort of analysis because we'll be looking at orders of program execution that can't possibly happen. And we are not going to worry about the possible values of P at different, the fact that P might have different values at different program points. We're just going to lump them all together. Nevertheless, we can get some useful information out of this. Does soundness mean it never produces false positive errors? If by positive you mean an error would be this particular object is never a value of P, right? When in fact it could be. It does not cause that kind of error. The kind of error it does cause is P could have this value when in fact it can't. So we're going to simplify Java considerably by just looking at a few canonical kinds of statements, namely creation of a new value with new, an assignment of one variable to another, a fetch of a field, an assignment to a variable, and an assignment of a variable to a field. And then we can take something like this, p.f.g equals r.f here, and we can convert that into a sequence of statements like this. A simple syntax-directed translation does the job. All right. Now, likewise, we can handle calls much the same way. So we have a call here, return foo. We create a new t, and we, sorry, no parentheses, and we call foo on it. So we'll translate this to the return value of foo is x.f, and we'll translate this guy here to r equals new foo, x equals r.g. In other words, the argument x here is r.g, and then s equals foo return value. So flow and sensitivity, I mean, it looks like all the return values from foo will be lumped together. That's conservative. It might or might not be useful depending on the program. Now, let's figure out what possible targets there are for the methods. And that's pretty easy. You can either look at the type of that P has, and that tells you what its static type is, which then presumably tells you that the particular method might be any of the possible methods that are defined for P or one of its subtypes. Or you can just look over the whole program and find all of the places, all of the types that are actually used. Now for arrays, what we're going to do in this to be conservative is we're just going to collapse all the arrays into a single value, into a single field, so that we aren't going to worry about whether I is equal to j when we assign from one to the other in this particular analysis. Now, the analysis I'm talking about is a simple, fairly old and simple analysis, not the best by any means, but nevertheless, it illustrates some of these ideas. So I'd like to compute this binary relation, whether a particular object flows to a value x. In other words, this particular object, and remember, objects are associated with each of the places where an object value can be created. Flows to x means that x can possibly get this value. Or if you want, you can do it the other way around. X points to object O, or might point to object O. So we'll do this in the usual sort of fashion. We'll look at the statements as facts about the flows to relationship. And this gives me, we now take a set of inference rules and apply them to these facts. And we get the set of facts that are inferred, that we start with, plus anything inferred by the inference rules. So whenever we see this, x, so we're going to write our facts like this. If we see this program, p equals new sub I, the ith new in the program of t, then we'll write that this way. We'll write assignment like this, and then we'll have the things for getting a field and putting a field to and from P. So these we can obviously derive by just going through the program and doing a simple syntax directed translation. And now we have some rules. If there is a statement, OI new P, that we've written OI new P, in other words, P is assigned from a new statement, that is from the ith new statement, then we'll say that object I flows to P. That's obviously true. If object I flows to R and R is assigned to P, then object I flows to P. Also obvious. If O sub I flows to A, and we put field F, we assign A to field F, and P is an alias of R, then if we get the field of R and assign that to B, then OI flows to B. And then we have this transitivity thing. If OI flows to X and to Y, then we say that X and Y are aliased. So we get this bunch of rules like this, these OI flows to rules. And what does this mean? Well, it means if we decide that O flows to Y, then all we know is that one of the possible values of Y is O. And this isn't terribly useful necessarily. It just tells us something that might happen. And again, what we're going to be interested in are things that don't happen, that definitely happen, right? Or don't happen. And unfortunately, the fact that O flows to Y does not mean that definitely O will flow to Y. It means that there's a statement somewhere in the program that could cause this to happen. That statement might or might not get executed, and it might or might not get executed before a statement where we're interested in whether that has happened. So what we're interested in are places where the analysis does not infer that O flows to Y. And if we are careful in our analysis, then if the inference does not happen, then it means that that there is no possibility of, in other words, if our system is sufficiently complete, then that fact tells us, the fact that there is no inference tells us that in fact O will never flow to Y. Okay, so that's good. And we likewise apply the same arguments in determining whether two pointers can point to the same thing. If we say yes, if the analysis deduces that they can, then we say, okay, they might point to the same place. That's probably not terribly useful, but if it says they can't be aliased, that's good. That allows us to do, for example, the non-overlapping heap fields. Now, using these inferences, just like a set of logical inferences, you can get all of the, I mean, basically what I've shown you in the preceding slides is a logical system that allows you to generate all these possible inferences about what might be the case. And we can go through that by just applying those inferences until we run out of possible inferences to make. And it turns out there are a finite number, sort of the number of possible objects times the number of possible destinations, that generating those inferences will eventually terminate. So, for example, if we have inferred from this preceding example, we will be able to infer that O2 flows to V. So O2 is initialized here, and we'll determine that it can flow to V. Why? Well, because it can flow, let's see, how does this work? It can flow to it can flow to y.f, and w.f can be alias to y, and therefore it can flow to v. So we'll decide that. But there's no way to infer that object 1 flows to v. That's this guy here. And therefore we know that that v will only be can only be of type bar. It can't be of so x nu x. It cannot be a foo. So when we thus, if we cast to type bar, everything will work, and we can throw away the cast. Yep, that is to say, our compiler can throw away the cast internally. So that's an example. This is just a quick overview of how this works. We get a bunch of assertions. We find all the consequences of the assertions. And when we're done, we're done. Now, you might wonder, how long does this all take? Well, I sort of hinted, because you look at the number of O's here, the number of possible objects, the number of possible destinations. And then you have to do some work, because you have to propagate values through all the possible destinations. This turns out to be, if you do the math, this turns out to be an n-cubed algorithm, which isn't great, but there are in fact faster algorithms. But you know, if you've got enough computer time, you can get some useful results out of it. And of course, that's the worst case. N-cubed is the worst case. In the average case, might be something is generally something considerably smaller. All right, so that's just one example of a kind of analysis, advanced analysis, that you can do to improve the performance of programs, to check their correctness and so forth. And it works by deducing things that could possibly be true in such a way that anything you can't deduce must be false, and then using that information about what must be false to improve your program. All right. Now we're going to move into something completely different, but first I will wait for if anyone has some final questions. Another thing I didn't cover, obviously, was the algorithms that you use to generate all of those, to efficiently generate all of those inferences. That's an interesting question too, and you're welcome to pursue it. But we're not going to do that here. All right, let's go on. Now this is this is no longer static analysis. This is storage management, runtime, a purely runtime issue. Now, as you know, there's no explicit way in Java, unlike C and C++, there's no explicit way to, to deallocate memory. But you know that memory does become useless, as for example here, where I've created a list of items and I return the tail of the list, meaning that the first element of the list, the one containing 3, is now hanging in the wind. You know, I mean, it just doesn't, or blowing in the wind, whatever it is. There's nothing that can ever get to it again, so it can never change, and it can never influence the further execution of the program, and it's completely useless. So what we do at this point is that the Java runtime somehow keeps track of all of this and throws away this useless storage eventually. Similar techniques are used in Scheme, in Python, and in, well, it's become a trend in modern languages to do this kind of automatic collection. of recyclable objects, which we call garbage collection. That's a technical term, by the way. So there are various ways of doing this. Various ways you could set your machine, your compiler and runtime system up to do this. Probably one of the oldest ideas is reference counting, where we simply keep track of whether there's anything pointing at our object. So we annotate every object with a reference count, counting the number of pointers to that object. So off here on the side, we have a couple of what are called roots. That is, variables that the programmer can directly mention, X and Y, and that might contain pointers. Each object, these are the objects on the heap, each object contains a counter at the beginning that says how many things are pointing at it. So in this particular case, one root is pointing at this object. One object is pointing at this second object. So this object over here is pointing at this object here. Now, when I do an assignment and so forth, when I do an assignment of to Y, assigning X's tail to Y, now all of a sudden Y is pointing here. And as a result, there are now 2 pointers to this object. And we count there. If I then assign Y to X, so that X is now pointing here, the result of that is that X is no longer pointing to this first object, the object it was pointing to originally. And so that object now has no more pointers to it. It now has a reference count of 0. Whereas this object here, the second object, now has 3 pointers to it. Now, because this guy has a reference count of 0, the runtime system, which is keeping track of these counts, knows at that point that this object here is now garbage. There's no possible way the programmer is ever going to use that again. Therefore, we can get rid of it. And when we get rid of it, this pointer here disappears, as does this pointer here. So this object now has only 2 pointers pointing to it. This object down here has 0 pointers pointing to it. And you can see what's going to happen. We sort of go down iteratively. This is now garbage, so it goes away, causing the sole pointer to this object to go away, causing the sole pointer to this object to go away. And as a result, we have, in fact, this assignment has deallocated this entire sublist. Very neat, very convenient. Now, this is used in a number of places. I remember reading about Objective-C a long time ago, where at least at that time, they were using reference counting. I don't know if they still are. And there was actually quite a bit that was written in the documentation about the care and feeding of this kind of automatic garbage collection, because it doesn't necessarily, it has certain problems. And I'm sure that you all know by this time, especially if you've taken 61B with me, I'm sure you can notice one case in which garbage does not get collected, which is, it's the obvious case. Yes, loops, anything that, any circular structure does not get collected. And that's kind of bad because it means that, for example, a doubly linked list, which you don't necessarily think of as being circular, where you have links going forward and backward, well, that's now circular. And a tree in which you have pointers from nodes back to their parents, that's now circular. And of course, the problem with a circular list, as for example, would be the case here, if this item here pointed back to the beginning, there's under no circumstances, once you get rid of all the pointers from all the roots, all the pointers that the programmer can actually mention to those objects are still have pointers to them. namely circular pointers. And so the whole thing will stick around forever. And there's a considerable literature on how to deal with that, but a lot of it, but to a certain extent, it depends on programmers to break these loops, or it can depend on programmers to break these loops. There are some clever things you can do as well. Also, every single pointer assignment, like a simple x equals y, or y equals x dot tail, involves, so this one here, x equals y, involves decrementing an integer, incrementing another integer. In other words, it involves a couple of heap accesses, even though this assignment here is just a simple assignment of one variable to another. So that's a fair amount of overhead. And of course, there's a memory overhead, the fact that you've stored these reference counts in here. There are ways of dealing with all of these things. For example, you can postpone when references are added or deleted in certain clever ways. You can keep reference counts, use very small reference counts. So at some point they just sort of overflow and become permanent, and then you have to do something else, but it uses less space. There are various tricks you can use, and this has all been discussed in the literature. Now, this is not the technique that is used for Java or many other of these places that now use a reference counting, in favor of other methods that don't have the particular problem of being unable to deal with circular structures. So we start with mark and sweep garbage collection. Another old idea, goes back quite a ways. Now, again, we start with these roots. And again, the roots are the variables that the programmer can actually name. In other words, the things that a program can directly get at. We start there and we do a graph traversal. I mean, after all, look at this structure here. This looks like a graph. You've got nodes, you've got pointers, you've got edges, that is. So it's a graph structure with a bunch of pointers into the graph structure. So we do a graph traversal, and we find every place that you can get to by starting at a root and following the pointers. That's called marking. Finding those things are calling marking. So we mark all of the storage that is reachable, that is, that you can get to from the roots, that a program can get to from the roots. So I mark them with stars here. Then I sweep through the entire memory. Now when I say I'm referring to the runtime system. Sweep through the entire memory. I find everything that hasn't been marked. And so here are the things that have been marked as I go through. Not exactly sure why E is not turning red here. And now that I've marked all that reachable storage, I sweep over everything. And, oh, there's E, finally. I had to get down to that point in the root. And then when we're done with all of that and we found all the marked structures, we can then go through memory. We assume the runtime system has enough smarts to be able to go through memory and at least determine when it's looking at an object in memory and how long that object is, how far it is to the next object. And having done all of that, we take all the things that have not been marked, all the things that aren't starred, and we turn them green. That is, we put them into some free list structure that from which we can reallocate them. And then we've done, where we now have cleaned out the garbage and we're left only with storage that is actually being used. And everything else, all the green parts, can now be reused for something else. So that's mark and sweep garbage collection. Nice and simple, really, when you come right down to it. And that's all very well, but it does have its little problems, or at least one might think of them as problems. For one thing, when I did this sweep state, when I did the marking, all I had to do was look at the storage that's actually being used. So mark follows pointers to storage that's being used. It ignores, it misses. In fact, that's the whole point. It misses all the garbage. But when I sweep, I have to sweep through all the garbage. In other words, the sweep stage, the amount of time required depends on how much garbage there is, as well as how much good stuff there is. Maybe you'd like to be able to, perhaps there's a way of avoiding doing that. And there is. We imagine instead that we're going to, oh yes, I'm sorry, and there's one other problem with this. You'll notice that these objects here are scattered throughout memory. This can sometimes cause problems. Those of you who've taken CS164 might be familiar with them. This can sometimes cause problems. And so it might be nice if we could collect all of this storage and squish it together. Of course, that creates its own problems, but sometimes it might be useful. It might improve locality, improve cache performance, that sort of thing. So this alternative method of garbage collection, called copying garbage collection, where we look only at the reachable storage, and as we do so, as we find it, we compact it, we move it into, we move it all together, we copy it from its previous area, from its previous storage into some new space. We call these areas from space and to space, or we copy from space into to space. These are from and to refer to what we call semi-spaces. In other words, each one of them represents maybe half or so of the total memory. And as we do this, as we go through copying things, we're going to have to update all the pointers that used to point to each object to point to the new objects. And to do this, we leave behind pointers in the objects we've copied. Pointers called forwarding pointers, saying what the new address of the object is. And then as we move things around, we will be, or as we move things, we will be updating the pointers to point to the new objects. Then when we're done, we will have copied everything that's good from space into to space. And now we can simply dump all of from space back into free memory all at once. And that's generally a fast operation. So we don't have to do a complete sweep. We just declare this is now free, one big free area. Or perhaps, well, there are other ways of doing it, but we can very quickly deallocate stuff. So the copied storage, in the process of doing this, the copied storage will be compacted. That is to say, the spaces between will be removed, locality will be preserved, and so forth. So here's how it works. Going back to our original example, this structure, which would be represented in memory like this. So the letters inside here represent pointers to the objects labeled up here. So object A, for example, contains 42. Object B contains pointers to object D and to object G, and so forth. All right, so let's see what happens. We're going to convert this from its original state here to this state, where the reachable objects have been, or here are some new objects, D, G, and or B and E. the reachable objects B and E have been moved to 2 space, and in the place where they used to be, we put in dashed lines here that indicate where they came from. Now, these 2 objects, B and E, we copied because we copied them from the roots. So we went to the roots, we copied the roots, B and where we find B and E, we copied those 2 objects here, leaving behind these forwarding pointers into 2 space, leaving behind these forwarding pointers from space to the new objects. So we copy their contents, the contents they used to have, directly. And you've noticed I use these little primes to indicate that these are new objects that we have copied. Now, having done this initial step of copying all the roots into 2 space, we now start over on the left side of 2 space, and we repeat this copying of pointers to the pointers that we find in memory. So we have a D, a G, and a D. So we start over here on the left. We copy object D. It's a new object. We haven't copied it yet. So we copy it down here. Copy its contents, 7 and G. And we leave behind a forwarding pointer as before. All right, what happens next? Well, next we come and we were here. So we now go and copy G, leaving behind a forwarding pointer and copying its contents into 2 space. That's easy. Now, so now how about E? Well, E points to D, and D has already been copied. We will keep track of the things that have already been copied. D has already been copied, and we know it's been copied to this location here, location D prime. So we update the D that used to be here in E prime, we update it to D prime using the forwarding pointer. Now we carry on. The next thing, we copy the 7. We don't have to do anything with the 7 because it's not an object. We see the G. The G has again already been copied, so we update it from its forwarding pointer. And likewise, we get this B here, which has already been copied, so we update it from its forwarding pointer. And here then is the garbage collected storage down here. And all of the pointers in it have now been updated to point into 2 space, into the corresponding objects in 2 space, the object corresponding to the old ones in from space. And now we just poof, get rid of 2 space altogether, and we're left with nice clean, we're left with a nice clean memory. We can continue to add new objects here at the end of from space, of the new from space, I should say, until things fill up again. Now, this does require a little bit of care or a little bit of help. So we have to know where these roots are. Where are the roots? And where are the pointer fields inside every object? That information has to be carried around somehow. So there are various ways of doing this. The compiler can help out by giving us a mapping between where you are in the program, the PC, the program counter, and where on the stack to find the various local variables, which are roots. The compiler or linker can also help, keep track of what all the static variables, the global static variables are, and so that the garbage collector can know about those. And this information can all be used by the garbage collector in finding out where to start and all that kind of thing. So we can also, every time we compile a new kind of object, we leave behind some information at runtime that tells where in that object you can find all the pointers. So obviously possible in principle. I'm not going to go into the details because they can get tedious and there are lots of different ways of doing it anyway. Now, for this to work in a naive fashion, you of course want to make sure that all the fields and all the variables have reasonable values in them so that you don't go chasing into uninitialized memory phantom objects that aren't actually there, and who knows what chaos you might cause by doing that. So that there is this cost involved in doing this, where we have to make sure, as we do not have to do in general for C and C++, that objects are initialized with some standard values like null, for example, or some existing pointer. However, we can actually get around that to a certain extent by, again, using this word that keeps cropping up in these kinds of analysis, conservative. You don't have any of the information in C, and yet you can still actually do garbage collection of C. And the way that you do this is that, first of all, it's easy to keep track. I mean, you have this storage allocator that's allocating storage for you. So it's easy to keep track of what storage has been allocated. And it's easy to keep track of how much space was allocated for each object, because you have to specifically ask for that amount of space every time you do an allocation. So what we can do, since we have that information, is that we can just guess that anything you're looking at that happens to look like an address somewhere in that, somewhere among that allocated storage, we'll just guess that it actually is a pointer to an object. And we'll guess that anything inside the object that whose length we know, right? If it looks like a pointer, it is a pointer. So we'll just make that assumption too. And now you can do just simple mark and sweep onto those assumptions. And it's conservative in the sense that you might get a bit of garbage that sticks around because something just happened to look like a pointer into it. But at least you won't deallocate stuff that definitely has pointers pointing to it. And this can actually be quite effective at for an ordinary mark and sweep garbage collector. There is something called the Berm-Weiser-Demers conservative garbage collector that you can use for C programs and C++ programs, actually rather widely used for doing this kind of thing. So you can actually do this sort of stuff for C, just not perfectly. Another technique we can use is what's called generational garbage collection. So the saying is that storage tends to die young. Think of Java. In Java, you cannot turn around without producing a bunch of objects, many of which are just going to stick around for a little while. Or Python, another example. Every time you return multiple values in Python, you create a tuple. So you've done some heap allocation potentially, depending on the implementation. So and then of course the tuple, immediately after you take the values out of the tuple and put them into whatever variables you were going to put them into, the tuple is now garbage. And that happens all the time. So you have this, you have this tendency that a lot of storage that you just because of the way object-oriented languages work, you have to create, a lot of that storage doesn't last very long. So what we can do is we can imagine dividing memory into young and old storage in a garbage collector that we did some years ago for the Smalltalk language, we referred to this as tenured and untenured storage, being as we are academics. And we can do do our garbage collection just on the young storage, and sort of assume that the old storage, since it's and then if we do enough garbage collections of a particular piece of young storage, we can then migrate it to old storage, sort of give it tenure, migrate it to old storage, and not look at it for a while. So that's pretty, now that's helpful because it means that the total amount of the total amount of work you have to do at each garbage collection can be made quite short, which is useful when you've got an interactive system, especially when you've got an interactive system where every time you do a garbage collection, things pause or could pause, and that's not, and that can be detrimental. But with generational garbage collection, very often you can cut these pauses down considerably in time. Now, if you think about this a little bit, you'll see that there are certain difficulties. For example, old storage can point into new storage. That can happen because you might update a pointer. You might assign a new pointer to something in old storage. So that means that in effect, the set of roots increases when you do that. So you have to have some way of keeping track of that. That's a complication in this sort of thing. And then every now and then, of course, eventually you fill up some of your old storage must become garbage eventually. And so every now and then you have to stop the world. You have to do a full garbage collection, an ordinary garbage collection. Nevertheless, this does significantly speed up the individual garbage collections. In fact, I believe that in the old days of Lisp machines at MIT, I think one of the techniques is rather than, you never do a full garbage collection. It just, when things are full, you crash and then restart. So that's a way of doing it. You know, it's one technique. So those are techniques for speeding up garbage collection. Here's another one, something called region-based allocation. So this is sort of a compromise between manual freeing and full garbage collection. And the idea is that the programmer creates regions or zones or something like that. And every time the programmer allocates something, it's allocated in a particular region. And then one of the things you can do to an object, to a region, besides allocate an object out of it, is to free everything in the region, just free everything all at once. So if I've got some calculation that's going to do a lot of heap allocation that I'm then going to throw away when I'm done with the calculation, I create a region to hold it. I do all the allocation in there. I never bother to garbage collect it or anything like that. But at the end, I just delete the whole region. So you have something like this. We have a pointer to a region. I allocate within it. And then I come to, maybe I have, this region would probably be a list of storage places. And then when I'm done, I execute a free that basically cleans out the entire region, and it's very quick. So this is a way of speeding things up. Of course, the problem with that is that this is just as would happen with manual freeing. It could be that stupid programmer that I am, I've allocated these things in a certain region, and then I deallocate the region and we have dangling pointers. Yes, one has to be careful about that, but it can be done. All right, I might add one other thing that I did not mention in the slides, which is that you can arrange that garbage collection proceeds in parallel with storage allocation. So every time you do an allocation, you can do a little bit of garbage collection. And there are various ways of organizing this. It's particularly useful when you're doing real-time programs, that is, programs that have to react within a particular amount of time. If you can spread out garbage collection so that you never get a complete pause, that's good. You can sort of guarantee, you can, if you're careful, guarantee that you only use no more than a certain amount of time to do a storage allocation. And therefore, you can guarantee that no more than a certain amount of time will elapse before you, between operations, and that therefore things will get completed within the necessary time limits of your real-time program. You wouldn't, after all, want to have the avionics software of an airplane say, I'm sorry, we're going to have to pause here for a few seconds while we do garbage collection in the middle of a thunderstorm or something like that, where it should be maneuvering. So anyway, these are all techniques that have been used to improve or to do storage management. It's kind of it's still an interesting subject, actually, because now we're moving to parallel computation, and parallel garbage collection is in which you are actually have two different processors, one of which is collecting garbage and one of which is creating garbage simultaneously. That's an interesting and kind of complex, error-prone thing to do. And nevertheless, when you've got parallel programs, it obviously might have some great use. All right, very good. That will do it for the material today. Hang on, let me see some questions in the chat here. Are regions optional, or does allocation have to take place in a region? Well, it depends on how you want to implement it. You could have a system in which some storage is allocated in some permanent large region, and another is allocated in specific regions, and that's been done, actually. The same thing as arena-based allocator. Yes, it is. It's the same. It's exactly the same concept. So those were two chat questions. All right. Anything else? Seeing no hands, I'm going to close this lecture, and I will see you on Thursday for our last lecture. In the meantime, please feel free always to contact us by email or Piazza about or Gitbug about problems that you might be having with Project 3. All right, have a nice rest of the day.